Okay, folks, it is that time of the morning, so I'm going to go ahead and get started. The Chem 101 code is 6565. Again, that Chem 101 code is 6565. The announcements for today, you do have a quiz that is due at 11:59 p.m. This week in lab, we will be doing the spectroscopy lab that we were supposed to do 2 weeks ago, and then also due on this upcoming Sunday, which I believe is the 20th. It will be homework number 4. What we'll be doing today is we're going to be building on what we were discussing last week, which was quantum numbers. Basically, the science or the observations and the principles that various scientists developed led to Schrodinger developing an equation that predicts the most probable location for finding an electron. And this equation produced 3 quantum numbers. That was the principal quantum number, the angular momentum quantum number, and the magnetic quantum number. The principal quantum number basically describes how far away from the nucleus the electron resides. The angular momentum quantum number describes the shape of the electron density map associated with that electron. And the magnetic quantum number basically describes which axis the orbital resides on. So it describes the orbital. Now, again, we're going to be building on those principal quantum numbers today, and we're going to start looking at how they are actually all embedded into the periodic table. And once we get through with the majority of the information today, the rest of the week is going to be spent developing electron configurations and applying quantum numbers to those electron configurations. So today we're going to be dealing with the principal quantum number and the angular momentum quantum number. First, we're going to talk about it from a 1-electron system, such as hydrogen. What does it look like? And then we're going to look at the multi-electron system. As we discuss these principal quantum number and angular momentum quantum number, what we're going to be doing is we're going to specifically be looking at the energy associated with the electrons in these groupings. Then, as I said, we're going to get into the periodic table arrangement, and we're going to be using Aufbau's principle to fill the lowest energy electrons in first. And to be quite honest, again, if you understand the periodic table is one of the most magnificent predictors out there, because it has so much information directly embedded into the periodic table. And the information it has in that's embedded in that periodic table includes all of the quantum numbers. So again, understanding the periodic table is huge. After we get through with the periodic, as we're doing this, we'll also talk about the Pauli exclusion principle, which is the main reason that we had that 4th quantum number that was not part of the Schrodinger equation, and that was the spin quantum number. Then we'll also talk about Hund's rule, which deals with degenerate orbitals. And then finally, we're going to start getting into electron configurations. When we start talking about the electron configurations, we'll look at the complete ground state electron configuration. Later on, I'll describe the difference between a ground state and an excited state. We'll talk about the noble gas core notation for an electron configuration. We'll talk about box diagrams, and we're going to talk about the quantum numbers and basically what it all means. So the very first thing is going to be talking about the energy levels. Again, if you'll recall, the principal quantum number, N, tells us the shell or the energy level. And for a basic hydrogen atom, well, it doesn't want to show it all. For a basic hydrogen atom, what we have is we have increasing energy on the left-hand side. You will notice that N of 1 is listed first. Then we go to 2, and the 2s and the 2p are of the same energy. Then we go to N is equal to 3, and the 3s, 3p, and the 3d are all of the same energy. And so what you will notice is when you're dealing with a 1-electron system, all L values are of the same energy. Now, what happens though when you get a multi-electron system? Let's think about that just from a general perspective. If you have the hydrogen atom, you have your proton in the nucleus, you have your electron in the shell, and the absolute only attractions and repulsions that are going on is between the proton in the nucleus and that electron in the shell. That is all that's going on, because you have one proton, one electron. Now, when you start adding multiple electrons, you will still have the proton-electron attraction, but when you start getting into multiple electrons, you then will also have electron-electron repulsions. So now you have more things going on in the same atom. Because you have a lot more going on within the same atom, what we see is that the subshells will no longer be of the same energy. In other words, the L values are not of the same energy. So you have your 1s, which is still the lowest in energy, followed by the 2s. But again, because we start dealing with a multi-electron system, the 2p is higher in energy than the 2s. Then you have the 3s, and the 3p is higher in energy than the 4s. And this, though, is where it gets interesting, because you would think, okay, 3s, 3p, 3d, but that's not the way it goes. The 4s is actually lower in energy than the 3d. So when you have a multi-electron system, again, the L values are not at the same energy. Now, this is important because this deals with Aufbau's principle. And basically, Aufbau's principle says your electrons will go into the lowest shell, the lowest subshell first. You will always fill from the lowest shell, lowest subshells. So this energy diagram is extremely important because it tells us how we're going to put the electrons in the atom. Now, you don't have to memorize this diagram, because once again, It's all embedded in the periodic table. Every single bit of that is embedded in the periodic table. Now, before I get into how those quantum numbers and that energy level is embedded in the periodic table, I want to just take a moment and look at the periodic table. This is the version of the periodic table that most people are familiar with. With the lanthanides and actinides being listed at the bottom. But if you follow the atomic number, you will see that the lanthanides are actually in period 6. And the actinides are in period 7. So if we're really looking at the periodic table, if we wanted to actually see the periodic table, this is the way it should be arranged. In this particular case, you have your inner transition metals, then your transition metals. This is how the main reason we use the prior format is because of space. So before I move back to one other thing before we get into how it's all embedded and the energy levels and everything else, I want you to think back, and I want us to talk about, well, actually, no, we'll use my next one. I want us to talk about orbitals and the number of electrons. Remember, your orbitals is m sub L. And there are 2 electrons per orbital. Okay. So on the left-hand side, except for helium, helium's the oddball, it does belong on the left-hand side. What you will see is the S subshell. From Friday's lecture, how many orbitals does an S subshell always have?
Is it 0?
0 is its m sub L value, but how many how many orbitals?
Oh, 1.
1.
1.
S only has 1 orbital. The S has only 1 orbital. And if 2 electrons can be in each orbital, that's why the S is only 2 elements deep. It's because an S only has 1 orbital and the maximum number of electrons is 2. So it can only be 2 deep. Next, over on the far right, you have the P. P means that if it's a p subshell, L is equal to 1. So how many orbitals, which is M sub L, are available?
3.
3. And if each atom can, or each orbital can have 2 electrons, 3 times 2 is 6. And that is why it is 6 elements across. Your D subshell has an M sub L of 2. I mean, an L of 2, excuse me, an L of 2. So how many M sub Ls is possible? How many orbitals is possible?
5.
5. So 5 orbitals means 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms across. And down here is your Fs, which means L is equal to 3. Your M sub Ls can be can equal
7.
7. And so that's, and 7 times 2 is 14. So that's why it's 14 elements across. Now, in addition to that, let's talk about how to get these numbers that you see. Oh, well. I call this it is not wanting to behave for me. I will refer to this as the excess, where X is equal to the period number. So this is what I'm referring to as X. So period number 1, S subshell, that's why this is the 1S. Period number 2, S subshell, that's why that's the 2S. Over here, I will refer to this as the XP block, where again, X is your period number. So since this one is in period 2, and it is the P block, that's why it's 2P. The Ds, now this group is called the X minus 1D group to get to its end value. So this one is in period 4. 4 minus 1D is equal to the 3 Ds. And this group down here is the X minus 2F group, keeping in mind where it belongs. That means this would be 6 minus 2F, or in other words, it's the 4F. Okay. So I mentioned the fact that the periodic table automatically tells you the energy. And so you don't have to memorize that energy diagram. If we read the periodic table from top left and then down, it's the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. And you'll see that as I was just, all I did was read left to right, top to bottom. And I've put those in the chat in that order because I want to illustrate that the periodic table already is discussing the energy. Because if we go back up here to that energy diagram that I gave you in the chat, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. That's supposed to be the 5s. That's got a typo. 5s, 4d, 5p, 6s. It's already there. You don't have to memorize this diagram. The periodic table already has it for you. In other words, the periodic table is already set up to follow the off-ball principle, which means you're going to put electrons in the lowest shell, lowest subshell in energy first. You don't have to memorize it. It's already there. Now, before we get into doing electron configurations, the next thing we need to do is talk about Hund's rule. Hund's rule says when you have a set of degenerate orbitals, you'll place one electron in each orbital before pairing. Basically, you'll have a set of degenerate orbitals anytime you're talking about a p subshell, a d subshell, or an f subshell. Basically, you have a set of degenerate orbitals anytime you have more than one m sub L value. Have a set of degenerate orbitals anytime you have more than one m sub L value. So just to illustrate this, I have a picture of the first, I think it's the first, well, I don't know if it starts with lithium. It starts with beryllium. This one is beryllium. Beryllium has 4 electrons. If you look at the periodic table, we start at the top. So that's why we started with the 1s and filled it up, which S can only have 2 electrons. Then we went to the 2s and filled it up because it can only have 2 electrons. The next one is boron. And with boron, you get your first P. So you put 1 in the P subshell, one of the orbitals. Then you get to carbon. So here's where we're talking about 1 electron going into each orbital before pairing. Then you have oxygen, no, excuse me, nitrogen. So you have 1 in each one. Finally, when you get to oxygen, you start to pair. And then you have fluorine and neon. Again, we do this because of Hund's rule. We do this because technically doing this is lower in energy than pairing electrons. Once you start pairing electrons, the energy will increase. And then again, the other principle was Pauli exclusion principle, which says no 2 electrons can have the same 4 quantum numbers. It is for this reason that we have the M sub s value. And it is for this reason that the maximum number of electrons in one orbital is 2. I was asked by Aaron, is there a difference if you start with a downward arrow, or is it the same as long as you stay consistent? Technically, it does not matter if you start with the downward arrow. It is just common practice to start with the up arrow. So most of the time you're going to see things starting with the up arrow, but it really doesn't matter as long as if you start with the down arrow, it's down arrow, down arrow, down arrow. You just don't want to pair them up. Okay, so this next periodic table I'm going to show you really does put into perspective all 4 quantum numbers on the periodic table. And the way we worked it is these would be M sub L value, or wait, no. I'm trying to make sure I have. These are your M sub L values. These are your M sub S values. And same thing over here. This would be your M sub L. These would be your M sub S's. Basically, the numerical value here represents your principal quantum number L. The letter, principal quantum number N. The letter represents L, because if L is 0, it is a S. If L is 1, it is a P. If L is 2, is a D. If L is 3, it is an F. Then the M sub L is based off of the L. And then you can have a plus 1/2, which will be for, in this case, period 1, or group 1. Group 2 would be a negative 1/2 spin. In the D, this represents your principal quantum number, the large letter or large number. The D represents your L. Your M sub L's can be anything from a negative L to a plus L. And then you have a plus 1/2 and a negative 1/2 spin. And again, the nice thing about the periodic table is it is already arranged according to energy. Any questions? I'm going to give you time to kind of draw the periodic table and get a gist of this thing, because it's going to be super useful when we start doing electron configurations as well as quantum numbers from those electron configurations. And yes, I am also recording this particular lecture because I know I'm giving you lots of diagrams to look at. Oops, didn't mean to make it small. When you get done, go ahead and give me an emoji of a thumbs up because I really, this is super important. So I want to make sure I'm not skimming past it too quickly. Okay. I see lots of thumbs up. So we are going to start moving forward. And we'll come, I mean, I will be using this essentially to develop both the electron configurations and the box diagrams and developing the quantum number, stuff of that nature. So that is where we're at, is we are to the electron configurations. And with electron configurations, we're going to be doing several different things. Number one, we will be doing the complete electron configuration. Basically, this one shows where every electron exists. In an atom of an element. We will talk about the noble gas configuration. And this one basically is a shorthand notation that uses the noble gases which is group 18, as a starting point. In developing the configuration. We will do a box diagram. And we will do a, we'll get the quantum numbers. So let's start out with good old hydrogen. Hydrogen's atomic number was 1, meaning that it has 1 proton, and in a neutral element, it'll have 1 electron. According to Aufbau's principle, the electrons have to go in the lowest energy shell and subshell first. Well, the lowest energy shell is the 1. The lowest energy subshell within that first shell is the S. And we represent the electron as a superscript. So again, here you have your principal quantum number N. You have your L representation, and the superscripts tell you the number of electrons. For hydrogen, we cannot do a noble gas configuration, so we'll have to wait for that one. But we can do a box diagram. It's called a box diagram because if you actually go on the internet, you're going to see it drawn as boxes. With the notation below it. So again, you have your N value, you have your L value, and you have your electron, and we typically put in electron spin up first. Now, because of trying to draw boxes and boxes and boxes, I do kind of cheat here in that I will just do it as a line and call it a box diagram, just to make it easier. Now, what this does is it tells you the M sub S value, and the line is going to tell you your M sub L value. With regard to the M sub S, if it's a plus 1/2, that would be spin up. If it's a negative 1/2, that would be spin down. So for quantum numbers, this 1 electron has a 1 for the N because they're always written as N, L, M sub L, M sub S. It has an L, N of 1. The L has to be 0 because it's an S. The M sub S is a plus 1/2. Now, what you've got to remember on M sub L is it's anything from a negative L to a plus L. For our case, it would be negative 0 to a plus 0, so it's just 0. So so hydrogen's 1 electron has the quantum numbers 1, 0, 0, 1/2. Helium is atomic number 2. So it has 2 protons, and in a neutral atom, it will have 2 electrons. According to Aufbau principle, you have to put them in the lowest shell, lowest subshell first, and an S subshell can fit 2 electrons. So helium is 1s2. Still, you can't do a noble gas configuration, but we can do a box diagram. You have your 1s, and there will be 2 electrons in it. The first one will go in, spin up. The next one will go in, spin down. So the quantum numbers for this, again, you can get N, L. The lines are going to represent our M sub L's, and our up and down represents the M sub S, the actual arrows. So the 2 electrons in helium, the first one is 1,0,0,1/2. The second one is 1,0,0, -1/2. Those would be the numbers that the Schrodinger equation would predict, other than the spin number. Let me skip a little bit and go to boron, which you actually saw when I introduced Hund's rule. Boron is element number 5. It has 5 protons and 5 electrons. It will start at the lowest shell, lowest subshell first, so the 1s. S's can have a maximum of 2 electrons because there is only 1 orbital when you have an S orbital or S subshell. And if you look at the periodic table, folks, it's 1s and you go all the way across 2. And now we're going to the second line, 2, and we come across the S subshell. You got to go through lithium and beryllium, so it takes up both of them. And then you go to the 2 P's, and boron is the first element in the P block. Now, what you will notice, folks, is if you take and add up the superscripts, they better equal the number of electrons. Now, finally, we can do a box or a noble gas diagram. Helium was our noble gas prior to the boron. And you will notice that helium and boron both contain the 1s2 in common. So what we do is we write helium symbol in brackets. Basically, this symbol says that I have everything helium has. Now we only need to list what helium does not have. And helium does not have the 2s2 and the 2p1. Now for our box diagram, it would be 1s, 2s, and then because there are 3 orbitals in the 2p, you draw 3 boxes or 3 lines. The 1s has 2, the 2s has 2, and the 2p had 1. We will pick up with this example on Wednesday, and we'll get a lot more complicated, and you'll see why the noble gas configuration is so nice then.